I'm Ahmed Daud, and in this session, we are going to start discussion on post-pruning. So, in the previous sessions, we have started the discussion on overfitting, that the biggest challenge we usually face when we are building a decision tree. We have discussed two approaches. One was the pre-pruning, and second was the post-pruning. Regarding the pre-pruning, we have done with all the stuff. We have seen the theoretical explanation, and we also have seen how we can implement pre-pruning part. First, we have to grow the whole tree. We have to grow the tree with putting some restriction on the growth algorithm of decision tree. Okay, so we pre-pruned. So in the case of pruning, we first grow the full tree, then we try to split the branches that are leading towards the overfitting or that are giving bad results on our testing data set. Okay, so before coming towards the today's session, first I want to elaborate here how we can calculate the Gini impurity of the whole tree. Let's say on the right side you can see this is the tree. This one is a tree which has four terminal nodes. Okay, so if I will ask you this can be a call as a tree T, capital T. If I will ask you what will be the Gini impurity of that capital T, how you can calculate? There is a very simple formula. I can say the Gini impurity of T, capital T, which is the whole tree. It is the weighted sum of Gini impurity of all leaf nodes, or you can say all terminal nodes. So sum of weighted sum of Gini impurities of all leaf nodes. Okay, this is the Gini impurity of the whole tree. Okay, so what is the intuition behind it? Why this Gini impurity of the whole tree can be calculated with by taking weighted sum of the Gini impurities of all their terminal nodes or leaf nodes? We will see in a while. Okay, so here you can see the formulation in which we are having here you can see this set of elements in which we have some blue points and some red points, 20 points belonging to blue class and 15 points belonging to red class. And this is the formulation of Gini impurity 1 minus sigma p I square. Okay, so if I will ask you what is the Gini impurity of that set of elements, you can easily calculate, and this is 0.49. Okay, now again, if I will ask you what will be the Gini impurity of these, you can say this one, this set of elements in which there are some boundaries. Okay, and some decision boundaries like this one, where some boundaries are present. What is the Gini impurity of that set of elements which have some partitions? So how you can calculate? You can easily calculate the Gini impurity of each partition. Okay, then you will see how much the proportion of that partition with respect to the whole data points that exactly be equal to their weight. Like if I will show you here, sorry, like here you can see, if I will say that this is the partition number 4, this one, in that there are 7 blue points and 3 red points. Okay, so there are total 35 points in the whole set. Okay, and if I will ask you what is the proportion of this partition number 4, you can say that there are 10 points present in that, and total points are 35. 10 over 35 will be the proportion of that particular transition number 4, partition number 4. Okay, so you just have to multiply the Gini impurity with that proportion, and in that case you can calculate the Gini impurity of that partition with respect to whole points. The same case you will do for each partition, and then you will add up all the whole Gini impurities with their proportions or with their weights. Okay, like I did here. Here you can see Gini impurity of partition, which has 6 data points and out of 35. here by summing, this you can call as a weight of that partition. This you can say that the proportion of that partition in whole 35 points or in whole data set, and whatever you can say. Then this will be the weighted sum of another partition, the Gini impurity of the another partition and their weight multiplying with their weight, Gini impurity of another partition multiplying with their weight, and Gini impurity of another partition multiplied by weight 8, and then the sum up, this will be 0.43. And this is exactly the same that I was discussing in that case. It is the weighted sum of Gini impurity of all leaf nodes. So all leaf nodes here are representing the whole partitions. Okay, like when you are doing some splitting on the basis of some rules, you are actually trying some decision boundaries in the data set, and your leaf nodes are representing some partitions. Like here this partition, this leaf node is representing the partition number 3, this one. This leaf node number 4 is representing this partition. This 6 is representing here this partition, which has 8 blue points and 3 red points. And the last leaf node 7 is representing this partition. Okay. And you can easily calculate the Gini impurity of the whole tree, or you can say Gini impurity of the set of elements which have some decision boundaries, or which has some partitions, simply by sum weighted sum of Gini impurity of all their leaf nodes. So this is about the how we can calculate the Gini impurity of the whole tree. Now we will come back towards the session that about today's session, which is the post pruning, and we will see how we can carry out the process of post pruning. So first of all, as from the word you can get an idea, post pruning. First, we have to grow the full tree. Then we will prune the branches that are leading towards the overfitting or that are giving some bad results on our testing data set. That's why it is called post pruning. Okay. After growing of the tree, then we will do pruning. So let's say this is the fully grown tree. Now we will prune the branches of that tree that are leading towards the overfitting. Okay, so there is a one formulation that we will use in that particular session, which is alpha is equal to r of small t minus r of capital T divided by t bar minus 1. On the basis of that particular formulation, we will do post pruning process. Okay, so this is the tree, fully grown tree. How we will use that alpha formula? We will calculate the alpha value of each non-terminal node, and then we will prune the branches of that particular non-terminal node which has less value compared to the all other non-terminal nodes. What is the intuition behind that alpha formulation, how it is derived, we will see in the coming session. But for now, you should consider just that formula. And regarding the there you can say the terms that are involved in that formulation, we can discuss here. Okay, so what is meant by r of small t? It is the impurity of the root node. What is the r of capital T? It is the impurity of the whole tree. What is meant by t bar? It is the number of terminal nodes. Okay, so for a while, let's say you here have to calculate the Gini impurity of that particular non-terminal node. How you can calculate? You can consider that the branches of that non-terminal node as the full tree. Okay, you can see this is the subtree of that green tree. This red tree is a subtree. Okay, so this is the root node of that subtree which has Gini impurity r of small t. And what is the Gini impurity of the whole tree? If we will call this as a t, then Gini impurity of the whole tree will be r of capital T, and which will be the weighted sum of their leaf nodes, or you can say terminal nodes. How many terminal nodes involved in that? There are 4 terminal nodes. Okay, so you got an idea about these terms. Now you can see that how we can calculate the alpha value for each non-terminal node easily. Okay, now what is the intuition? A little bit we can do discussion on that. Let's say r of t minus r of capital T, it is actually mean by This can you can call it as the decrease in impurity. Okay, when you have done this splitting into some four nodes like this one. Okay, you have performed some splitting, you have converted this one node into four terminal nodes. So by splitting one node into four terminal nodes, how much the decrease in impurity, the ratio of decrease in impurity, and how number of nodes we have added to the whole tree, this ratio is called alpha. Okay, in other way you can call that uh, we have converted one node into four nodes. Previously when we were growing the whole tree, at that particular stage we are having just on this side we are having one terminal. Then as our algorithm is performed splitting on that particular node, it has converted into two nodes, again it has converted into two nodes, and it has here created four terminal nodes. So we can say that one node is converted into four terminal nodes. And in other words you can say that instead of we have converted one node into four nodes. So how many number of nodes we have added? 4 minus 1, 3 number of nodes we have extra added to that particular whole tree, that particular whole tree. Okay, so this as you know that the more number of leaf nodes, more number of terminal nodes, we can say the more complex the model is, or the more complex the decision tree is. Okay, so what is meant by that? It is actually alpha value explain about the splitting point, that how much this splitting is decreasing the ratio of how much it is decreasing in impurity, and how much it is adding the complexity, how much it is adding the number of nodes into the tree. This is actually alpha value. Okay, alpha value you can say that if when you are calculating the alpha value for each non-terminal node, the node which is having minimum alpha value, you can call it as a weakest link. Okay, or you can say that this particular splitting is less important compared to all other non-terminal nodes, because there can be two reasons. That's why we can say that it is unimportant. One reason can be that it has less decrease in impurity, and second reason can be that it is adding more complexity compared to the other non-terminal nodes. Okay, that particularly the intuition behind alpha, and about the derivation we will discuss in the coming session. So now we will do an example, then you will get a more precise idea how we can carry out the process of post pruning. First of all, we have here a fully grown tree. This is the fully grown tree. We mark this as a T1. Okay, we say that this is a tree T1. At the start we can say that this has alpha value 0. And what is the impurity of T1? This will be weighted sum of their leaves. Okay, so this will be the weighted sum, and we consider that it is 0 for a while. Okay, then what we do, we calculate the alpha value for each non-terminal node, like 1 2 3 4 5. There are 5 non-terminal nodes. We calculate the alpha value for the whole number of for all non-terminal nodes, and the non-terminal node which have minimum alpha value compared to all other non-terminal nodes, we will prune the branches of that particular non-terminal node. Okay, we will prune the branches of that non-terminal node, like here in the case of this tree, this particular node is giving the minimum alpha 0.005, which is less than compared to the alpha values of all other non-terminal nodes. So we will prune the branches of that non-terminal node, and the tree with that particular the tree with pruned branches will be called as a tree T2. Okay, and this T2 will have the alpha value 0.005, which is the same uh, uh, as the alpha value of non-terminal node which is recently pruned. Okay, which is the recently pruned, the alpha value of that non-terminal node will be the alpha value of that particular tree T2, which is we have created when we have pruned the branches of recently pruned branches of that particular non-terminal node. And the weighted sum, again the weighted sum of all their here you cannot say that child, you can say weighted sum of 5 leaves. Okay, you can say 5 leaves. Again, you will perform the same process, calculate the alpha value for all non-terminal nodes, select the non-terminal node with the minimum alpha value and prune the branches of that, and you will get another tree, which is tree 3, which have the same alpha value 0.012, which is the alpha value of that non-terminal node which is we have pruned. Weighted sum of their childs, it will be the Gini impurity of this whole tree T3. Again perform the same process, again you will get the another tree which is T4. Again perform the same process, as is only one non-terminal node, and which is having alpha value 0.25. You cannot compare it with anyone because there is just one non-terminal node. So you will prune the branches of that non-terminal node, and you will get another tree T5, which is just of having one node, which is terminal node having alpha value same of the non-terminal node which we have pruned recently 0.25, and gene impurity of that particular root node. It is the root node, so for a while we can say that it is just the root node, we can ignore this one. Okay, now how many? T5, T4, T3, T2, T1. We have 5 trees in which we have ignored that T of 5 tree because it is just the root node. So total we have 4 trees here. Here you can see clearly. Okay, so T1, T2, T3, T4. T1 when the alpha value was 0, T2 when the alpha value we have pruned the branches of non-terminal node which has alpha value 0.005, which is less than compared to all non-terminal nodes. So this in that way we get another tree which is T2, and again we have pruned the our tree T2 on the basis of minimum alpha, we get T3. Again pruned, we get another tree which is T4. Now we have here finite number of alpha values 0, 0.005, 0.012, 0.018. And you can see that there is some sequence in that. All alpha values are increasing order. Your impurity is also continuously increasing here, and in that sense you can also see your trees here. Your trees are continuously decreasing their complexity, like T1 is more complex compared to T2, T2 is more complex compared to T3, T3 is more complex compared to T4. Okay, and it is quite obvious, like you have decision tree in some ordered form because you have pruned the branches of that non-terminal node which is weakest compared to all present non-terminal nodes. Okay, so you are creating a number of trees in some ordered form. Okay, you have first pruned the alpha value which is 0.05, which is less than compared to all other alpha values. Then you have pruned the alpha value which is pruned the branches of non-terminal node which has 0.012 value, which is less than uh, the alpha values of other non-terminal nodes that are present at that particular position. Okay, so you have here number of trees, or in other words you can also say that you have finite number of alpha values. Now if I will ask you uh, draw a tree, or build a tree which has alpha value 0.012, how you can get that particular tree? First you have to start from fully grown tree. You have to pass the data set to your tree, and without putting any restriction on the growth of algorithm, you have to grow the whole tree. Then you will prune the tree with respect to minimum alpha, the same algorithm that we have followed. Then you have to stop your process of post pruning when the pruned tree has minimum alpha value greater than 0.012. Hence you can get easily your tree which is having alpha value 0. Equal to 0.012. We can see here you will start from the fully grown tree, and then you are keep on pruning with respect to minimum alpha. You get another tree which is having minimum alpha 0.012. T3 has minimum alpha 0.018. Okay, so minimum alpha of T3 is 0.018, which is greater than the your specified value, which is 0.012. You are finding the tree which is having a value 0.012, and I said that stop at the particular position at the particular tree which has the minimum, which has the minimum value of alpha greater than your mentioned value. And you can see here that 0.012 is less than compared to the minimum value of that particular T3. Okay, so this will be the tree. T3 is equal, you can say the alpha value is equal to 0.012. If you will pass, you will get a T3, because the minimum value of T3 is 0.018, okay, which is greater than the your specified value. So in that way you can get your tree against each alpha value. So here you have four alpha values, you can get the four decision trees. Okay, so you will pass alpha value 0, in that way you will get the fully grown tree. Then again you will pass another alpha value, you will get another tree. And you are quite familiar with that, like when you will pass t1 is equal to tree which has alpha value 0.02 5005, you will get obviously that tree. Okay, because that tree has minimum value 0.012, which is greater than your specified value. So in that way you can again get your trees. Then you will calculate the score on the testing data point by using these trees that you have created with respect to the your finite range of alpha values, or with respect to the alpha values you have gotten from your process of post pruning. And again you can get the trees, these same trees here, when you will pass the alpha values. Okay, and then you will calculate the score on the testing data points, and which tree will give you the best score, you will consider that as a best decision tree. Okay, this is the actually process of post pruning. First you have to grow full tree, then you have to prune the branches in some ordered form in the way of minimum alpha value, and select the alpha value, or the select the tree which is giving you the best score on the testing data points. Okay, this can be called as your best possible decision tree with respect to that particular data set. Okay, in that way you can do post pruning process. We will see here an example. Let's say this is the decision tree of the iris data set. You can see here this is the fully grown tree. I will consider that fully grown tree as a TT1. At the start, I can say that this is the tree T1, T1, okay, which has alpha value 0.0 and impurity is 0.012 at the start, which is the weighted sum of their leaves. And when you will add the Gini impurity of their leaves, there are how many leaves there are? 1, 2, 3, 4, 5, 6, 7 and 8. When you will do the weighted sum of their leaves, you will get your Gini impurity of that Tt1. Okay, so then you have to calculate the alpha value for each non-terminal node. Like this is non-terminal node, this is non-terminal node, this is non-terminal, 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 non-terminal. Sorry, this is not non-terminal. Okay, so you will calculate the alpha value for each non-terminal node of tree T1, and you have to prune the branches of non-terminal node which has minimum alpha. Like in this case, this node number 4, node number 14, sorry, has the alpha value 0.005, which is less than compared to all other non-terminal nodes. I will not calculate the alpha value for all the non-terminal nodes. I will calculate just for the node number 14 so that you can get an idea. And remaining, if you want to, you can calculate by yourself. And regarding the implementation, I always say that it is when we are importing some library, it is quite simple. So in that case, in the case of post pruning, again we will import some methods of sklearn. Okay, so but to get the theoretical concepts, you can calculate by yourself alpha value of all the non-terminal nodes. So if we will consider that particular node number 14, how we can calculate the alpha value? So we know the alpha value has that formulation. If we will consider that node number 14 as a root node, and there are two non-terminal, there are two terminal nodes of that root node, so we can easily calculate like here the Gini impurity of the root node, which is 0.05, here 0.059. The Gini impurity of the whole tree, if we will consider this as a whole tree, which it will be the weighted sum of their leaves, which is here you can see. If I will calculate here, this will be the R of capital T. Okay, so weighted sum of the their childs, or sorry, their leaves. Then this will be the decrease in impurity. The impurity of root node, impurity of the whole tree, minus whole tree. This will be the decrease in impurity of that particular subplating. Okay, with respect to that particular subplating. If I will say that how much the decrease in impurity this particular subplating has compared to the whole tree. So you simply multiply the proportion of that node number 14, the proportion of that node number 14 with respect to whole, uh, you can say, with respect to whole tree or with respect to whole data points. And we also have discussed that decrease in impurity in that particular hyperparameter. If I will show you here, like in this mean impurity decrease, we have considered here, first we calculate decrease in impurity, then multiply with their proportion, how much the weight of that particular node for which we are calculating the decrease in impurity. So the same, this node number 14 has the sample 33. So we will here multiply 33 by 105 with the decrease in impurity. This is the impurity of the tree that we have considered. This is the impurity of the tree. This is the impurity of the root node of the tree. And this whole will be the Gini impurity, decrease in Gini impurity. Then we have multiplied with the proportion of that non-terminal node with respect to whole number of points. And we get here, this is the 0.006. This is the decrease in impurity with respect to whole tree. So alpha will be 0.006. How many number of branches or how many number of terminal nodes for that particular tree? For that particular tree, how many number of uh, uh, leaf nodes? 1 and 2. So there will be t bar will be equal to 2. So here will be, according to formulation, 2 minus 1, and alpha will be 0.006. Okay, in that way you can calculate the alpha. So here you can see I have actually approximated. So 0.005772, I have approximated that value equal to 0.006. That's why I have here 0.006. Okay, in that case. So here you will calculate the alpha value for each non-terminal node and prune the branches of the terminal node that is having you can say minimum alpha value. Okay, and you will get another tree which will be here, you can say tree T2. Okay, again you will prune the branches of the tree which has minimum alpha. So this tree T2 has alpha value 0.005772, and the impurity of this T2 is 0.018. Again, you will prune the branches of non-terminal node with minimum alpha. You will get another tree which is T3, which will have alpha value this one and impurity this one. Again, you will prune on the base of minimum alpha, and you will get another tree which will be a T4, and this T4 will have this alpha value and this 0.05 Gini impurity. And keep in mind this alpha value, it is the alpha value of node number 7, uh, or you can say the alpha value of the non-terminal node which is recently pruned. Again, you will prune the on the base of minimum alpha, and you will get another tree T5 which is having this alpha value. Again prune, you will get again another tree T6, and this will we have this alpha value and this impurity. Again prune, you will get another tree which will have this impurity alpha value and this impurity. Again prune, you will get another tree which has this impurity alpha value and this impurity. And here you can see at the end you will get the root node. Root node always have the Gini impurity of the whole data set, which is 0.664, and here you can also see you have the impurity 0.664. Okay, so we will ignore that because it is just the root node. So how many trees we have total? We have here uh, 7 trees: T7, T6, T5, T4, T3, T2, T1, that have some order. Okay, we can say here we have tree T1, T2, T3, T4, T5, T6, and T7, and T8 we can ignore that because it is just the root node. Okay, so we have 7 trees, and all the trees are in some order because as we are increasing our index, our tree is becoming simpler because we have pruned a lot of branches. In the case of T7, T7 will be simpler compared to all other trees, and T1 will be the complex compared to all other trees. Okay, so we will analyze the tree, all 7 trees, on our testing dataset, and which tree will give us the best score on the testing dataset. We will select that particular tree as our optimal tree or as our good tree according to our use case. Okay, in that way we will do post pruning. First we will grow whole tree, then we will prune the branches with respect to some minimum alpha value, and then we will uh, in that way we can get a finite number of alpha values. By using that finite number of alpha values we can get the trees again. Okay, and number of some number finite number of trees, and when we will calculate the test score on the testing data points by using these trees, which tree will give us a good score, we will consider that tree as our good tree or as our optimal tree. This is actually the whole process of post pruning. And regarding the one concept, how alpha formulation is derived, what is actually intuition behind the alpha, we will consider in the coming session. We will try to explore that a particular you can say that particular concept also. And after that we will jump towards the part of implementation, and we will use how we can do post pruning by using sklearn. So for now,